A massive machine moves through a substation at walking speed. Crews watch every cable, every wheel, every inch of clearance. The move looks temporary. The machine is anything but. Large power transformers sit at some of the most important junctions in the American electrical system. They connect generating stations to high-voltage transmission and help move electricity across the bulk power network. In July 2026, the National Laboratory of the Rockies said that more than 90% of power consumed by Americans passes through high-voltage transformers at some point. Yet the largest of these machines are not products a utility can order from a catalog and collect the following week. They are engineered around voltage, capacity, impedance, protection, physical layout, and the requirements of a specific site. A unit that fits one location may not be a practical substitute at another. That creates a quiet contradiction at the center of the grid. Electricity can move across a continent almost instantly, but one of the machines required to move it may take years to design, manufacture, test, transport, and install. Why can such a familiar piece of grid technology still be so hard to replace in the United States? The basic job of a transformer is familiar. It changes voltage. At a generating station, a generator step-up transformer raises voltage so power can enter the transmission system. Elsewhere, other transformers help connect different parts of that system and eventually bring voltage down for regional and local networks. But the simplicity of that principle hides the specificity of the machine. The required voltage is only the beginning. Engineers also have to account for capacity, impedance, protection systems, cooling, physical dimensions, connections, clearances, and the electrical behavior expected at the site. The substation has its own layout. The foundation has limits. The surrounding equipment has fixed interfaces. Transport access may constrain the dimensions of the unit before manufacturing begins. A replacement has to work electrically and fit physically into a system that was built around particular assumptions. This does not mean that every transformer is unique in every detail. Designs can share components, practices, and specifications. But large power transformers are not interchangeable commodity boxes. A utility cannot assume that any large spare will match any open position on the grid. That is why replacement starts long before a truck reaches a substation. It starts with engineering. Once the design is fixed, the order enters a factory sequence that depends on specialized material, specialized workers, and test equipment that cannot simply be bypassed. A large transformer begins as a design, but it becomes real through a long sequence of physical work. The magnetic core is built from layers of electrical steel. Around that core, conductors are formed into windings. Copper has to be arranged with precision, insulated, supported, and connected for the voltage and capacity the machine is expected to carry. Among the specialized inputs identified by the Department of Energy are grain-oriented electrical steel, continuously transposed copper conductor, and specialized insulation materials. These are not decorative choices. They are part of the electrical and mechanical structure of the transformer. Winding is followed by core and coil assembly. Large components have to be lifted, aligned, compressed, connected, and placed inside the tank. Insulation and internal clearances have to remain controlled through every step. The assembled unit then goes through drying, oil processing, and other preparation before it can be shipped. Testing is not an optional ceremony at the end. The Department of Energy's 2024 Resilience Report lists high-voltage testing as part of the specialized manufacturing process. Test bays, instruments, and trained personnel are therefore part of factory capacity too. A production line cannot solve the bottleneck by pushing an unfinished machine out the door. The workforce is equally specific. The supply chain depends on engineers, winders, assemblers, welders, test personnel, and field crews. Adding floor space does not instantly create those skills. A new building can be completed before a new workforce is ready to design, assemble, inspect, and test the largest units. This is the first reason the replacement clock is long. A transformer is not one fabricated shell. It is a chain of dependent operations. The core cannot be assembled before the material arrives. The windings cannot be treated as an afterthought. The test hall cannot certify a unit that has not completed the earlier stages. And every factory slot is competing for many of the same materials, workers, and machines. Lead time is often discussed as if it were a single national number. It is not. Different voltage classes, designs, manufacturers, and projects can face different schedules. The most defensible recent example comes from a July 2026 National Laboratory of the Rockies analysis of the hydropower supply chain. In that context, procurement for a typical 100 megavolt ampere large transformer was about 2.5 to 3 years. Some extra high voltage units could reach 5 years. 5 years is not the rule for every transformer. It is the far end of a specific and difficult class of projects. The same laboratory reported that prices in the hydropower large transformer market it studied had risen about 80% in 2025. The Government Accountability Office's August 2023 report identified long and increasing manufacturing lead times, limited capacity, labor shortages, and material shortages as major challenges. Domestic manufacturing does exist. The problem is not that America makes no large transformers. The problem is that only a limited number of facilities can produce the largest extra high voltage units, while demand reaches across utilities, generators, and major grid projects. Materials add another layer. In 2024, the Department of Energy reported that the majority of grain-oriented electrical steel used in U.S. large transformer manufacturing was not produced domestically. The 2026 hydropower analysis described roughly 80% import reliance for raw materials in the supply chain it evaluated. That does not mean 80% of complete American transformers are imported. It means the manufacturing base remains connected to an international material pipeline. Securing a factory slot, therefore, is only one part of securing the machine. When factory testing ends, the transformer is still not part of the grid. First, it has to move. That journey can become an infrastructure project of its own. Large transformers are constrained by mass, dimensions, bridge capacity, turning radii, rail access, permits, and the final approach to the site. The route that works for ordinary freight may not work for a machine carried on a specialized rail car or a trailer with many axles. The Government Accountability Office reported that a large power transformer can cost as much as $10 million. Moving one can add hundreds of thousands of dollars. The cost reflects more than distance. It can include route surveys, permits, escorts, cranes, temporary roadwork, rail or water transfer, and coordination among utilities, carriers, and public agencies. A port may be able to receive the machine, but that does not solve the inland route. A railway may carry it across several states, but the substation may not sit beside a suitable track. A highway may appear wide enough until engineers calculate bridge loading, corner geometry, and the space required for a multi-axle trailer to turn. The Department of Energy describes a separate last-mile problem after a transformer reaches a selected rail or road drop-off point. The customer must still plan the move to the final site. That route can require bridge analysis, road closures and detours, temporary relocation of power lines, specialized heavy haul equipment, permits, and cranes before the load arrives. Fort Randall Dam in South Dakota offers one documented example. The replacement transformer was manufactured in Germany. It traveled through Galveston, moved by rail to South Dakota, and was then positioned at the generating station. That route should not be treated as the standard journey for every American transformer. It shows how many systems can be involved in one project. Transport also changes how a transformer is prepared. Accessories may travel separately. The main unit has to be secured for movement. Once it reaches the site, crews still have to position it, complete assembly work, fill and settle the insulating oil, commission and test the unit, and prepare it for energization. The machine can cross an ocean faster than the project around it can cross the last stretch of road. That is the second clock in the supply chain. Factory time ends, but logistics time begins. The consequences of a transformer problem depend on where the unit sits, what happened to it, and what alternatives are available in the surrounding grid. There is no single failure story. Large power transformers face risks from aging and wear, extreme weather, natural hazards, and physical or cyber-enabled attacks on grid infrastructure. Those risks do not have the same probability, the same damage pattern, or the same response. Nor does one failed transformer automatically produce a nationwide blackout. The scale of the disruption depends on the location, the surrounding grid, the damage, and whether a compatible spare can be deployed. The important constraint is what happens when a suitable replacement is not ready for that site. Then the supply chain clock becomes part of the recovery clock. Engineers have to assess the damage and determine what can be repaired. If replacement is required, the utility needs a compatible unit, a feasible transport route, site access, crews, and cranes. Installation then includes assembly, oil filling and settling, commissioning, and testing before the unit can return to service. General restoration footage can make this process look fast because emergency crews move with urgency. Lines can be restrung, poles can be replaced, roads can be cleared. But those visible operations are not proof that a large power transformer can be replaced on the same schedule. The distinction matters. Grid restoration is a coordinated response across many kinds of equipment. The largest transformer may be only one element, but it can carry a manufacturing and logistics schedule that is much harder to compress. That leads to the obvious resilience question. Why not keep enough spare transformers waiting in warehouses across the country? Utilities do keep spares, and spare strategies are part of grid resilience. But a warehouse full of universal replacements is not a complete answer, because the machines are neither small nor fully standardized. Each spare ties up money, storage space, and transport planning. More important, compatibility has limits. A unit has to match the electrical requirements of the position and connect to the physical system around it. Voltage, capacity, impedance, protection, physical connections, and site layout cannot be ignored because an emergency has begun. A spare that is useful for one family of substations may be unsuitable for another. Even a compatible unit still has to reach the site and be installed. The spare removes part of the manufacturing delay. It does not remove bridge limits, crane requirements, access problems, or commissioning work. That does not make standardization pointless. Common configurations and shared specifications can improve compatibility and reduce unnecessary variation. They can make a spare strategy more effective without creating one machine for every possible location. As of the Government Accountability Office's May 2026 update, recommendations related to transformer resilience and supply constraints remained open while the Department of Energy continued work involving common configurations and specifications. The practical goal is not a magical universal transformer. It is a system in which more units can be sourced, shared, transported, and installed before a long delay becomes a larger reliability problem. The supply problem is not happening in a static grid. In June 2024, the National Infrastructure Advisory Council identified several demand pressures affecting transformer supply: electrification, renewable generation, grid expansion, and data center growth. These forces are not identical, and none of them alone explains the entire market. Together, they place more projects into the same constrained production system. The same 2024 report recorded lead time ranges of roughly 80 to 210 weeks for power and generator step-up transformers. That range is a dated market snapshot, not a universal schedule for every order today. But it illustrates the scale of the planning problem. A project that needs a transformer cannot assume the machine will appear after the rest of the work is finished. Replacement projects and expansion projects can therefore meet inside the same production queue. One is trying to preserve an existing capability. The other is trying to add a new one. From the factory's perspective, both still require engineering, material, labor, assembly, and testing before a unit can leave the gate. Generation planning, transmission construction, industrial investment, and large new electrical loads all have to account for equipment that may have to be ordered years before energization. If the transformer order comes late, the machine can become the pacing item even when financing, land, and other major components are available. Limited factory capacity is only part of the equation. The same projects are also drawing on engineers, winders, assemblers, test bays, raw materials, heavy haul carriers, specialized rail cars, cranes, and field crews. This is why the bottleneck cannot be solved by blaming one new source of demand. Data centers matter. So do renewable projects, replacement needs, electrification, generation interconnections, and expansion of the grid itself. The question is how to expand the pipeline without weakening the engineering and testing that make the equipment dependable. There is no single program that removes every constraint. The response is a portfolio of measures aimed at different parts of the problem. Federal and industry work includes supply chain analysis, common or shared specifications, spare strategies, investment in domestic capacity, and research into transformer designs that may be more modular or flexible. Each approach solves a different problem. Better supply chain visibility can identify where material or component shortages are forming. Common specifications can increase the chance that one design works across more than one site. Spare programs can reduce exposure to the longest manufacturing delay. Investment can add equipment and factory space. Training and retention can build the workforce required to use that capacity. Common specifications also have a boundary. They may reduce avoidable design variation, but they do not erase voltage requirements, physical connections, transport limits, or the conditions at a particular site. Resilience improves when more units are compatible, not when engineering differences are simply ignored. But none of these measures should be counted before it exists. A factory announcement is not the same as commissioned production. A new building is not the same as trained workers, qualified processes, and an operating test bay. A recommendation is not the same as a completed resilience program. ARPA-E's September 2025 workshop explored flexible, modular, hybrid, and solid-state transformer concepts. Participants considered whether such designs could reduce planning and commissioning time and reliance on large magnetic and copper materials. That is development work, not evidence that a universal replacement fleet is already deployed. The near-term challenge is therefore less dramatic and more difficult. Improve compatibility where engineering allows it. Keep useful spares. Expand material and manufacturing capacity. Train the people who design, build, test, move, and install the machines. Coordinate procurement early enough that transformer delivery is part of the project schedule, not a surprise at the end. These steps do not eliminate the physical sequence. They try to make it less fragile, more visible, and easier to repeat. America's electrical ambitions are usually described in terms of projects, new generation, new transmission, new factories, new data centers, and stronger resilience after disasters. Large power transformers reveal the physical chain underneath those plans. Before power can flow, electrical steel has to become a core. Copper conductors have to become windings. Insulation has to be prepared. Skilled workers have to assemble the machine. Test halls have to verify it. Carriers have to move it. Public agencies and utilities may have to clear a route. Crews have to position, connect, test, and energize it at the site. Money matters, but money cannot make those steps simultaneous. A permit cannot train a winder. A factory expansion cannot create qualified output the day it is announced. A spare cannot help every location if it does not match. A completed power project cannot use a transformer that is still waiting for material, testing, or a transport route. This does not mean the American grid is one machine away from collapse. It does not mean the country lacks manufacturing, and it does not mean every large transformer takes 5 years to obtain. It means that a small class of custom equipment can set the pace for projects far larger than the machine itself. The grid moves electricity at extraordinary speed, but the grid is built and repaired at the speed of steel, copper, insulation, labor, factory slots, bridges, trailers, cranes, and careful tests. The constraint is not a lack of ideas. It is the time required to turn raw material, engineering, labor, and logistics into one machine ready to carry power.